Hello and welcome to this brief presentation related to angular motion. The hands of a clock are subject to angular motion, and in an engineering context, a flywheel is subject to angular motion. This presentation will review the various angular motion equations. Firstly, let's consider some underpinning knowledge that's required to help understand the work we're going to review in this presentation. It is assumed that you've seen a previous presentation related to linear motion and the linear motion equations we derive therein. So these here are the equations, often called Newton's equations of linear motion, as angular motion is totally analogous to linear motion. Also velocity time diagrams, something again we reviewed in the previous presentation on linear motion, where we plot velocity in meters per second against time in seconds, as we'll be reviewing angular velocity time diagrams in this presentation. Also from a previous presentation we've considered radian measure, the S equals to r theta formula, where S is arc length, r is radius and theta is angle subtended. As in this work, our angular displacement will be measured in radians. We also need to be able to convert from degrees to radians and vice versa. And finally, we need to be able to transpose equations, again something we've covered in previous lectures. Here's a very brief review of the radian. As you mentioned in our previous lecture, the radian is used in high-level mathematics, and the radian simplifies both derivations and calculations at high-level study. So the radian is a property of a circle. So 1 radian is the angle theta, shown here, subtended at the center of a circle, O, by an arc length, S, shown here, whose length equals the circle's radius, R, shown here. So in other words, when S is equal to R, we have 1 radian subtended. So from the geometry, angle in radians, theta, is the arc length S divided by the radius R. The formula referred to as radian measure is arc length S equals to R multiplied by theta, where radius R is in meters or millimeters, and the angle theta is always in radians. And that's very important to remember. This diagram shows the relationship between degrees and radians. So we know from our previous work, in 1 revolution there are 360 degrees, but in terms of radians there are 2 pi radians. So in 180 degrees there would be pi radians, and in 90 degrees there's pi upon 2 radians. 270 degrees we have 1.5 pi radians, or 3 pi upon 2. So you often find angles in radians can be expressed in terms of pi radians for accuracy. And purely for visualization, because we often think in terms of degrees, 1 radian is approximately equal to 57.3 degrees. That essentially relates to the fact that there are 2 pi radians in 360 degrees, or 1 revolution. That's very important to remember. Here are the conversions, again we reviewed in our previous presentation, from degrees to radians. I'm showing the unity bracket here. We stated on the previous slide that there are 2 pi radians in 360 degrees. Of course that could be simplified to 1 pi radian in 180 degrees, and that's the conversion I'm showing here in the unity bracket. And again, remember these are cancelling unity brackets. So if I'm converting from degrees to radians, then my unity bracket is pi upon 180, because I need to cancel a degree on the top line with the degrees on the bottom line. An example calculation shown here for your reference. And if I'm converting from radians to degrees, then I invert the unity bracket. So in this conversion, I need to cancel the radians in the top line with the radians in the bottom line. And again, an example of that conversion is shown here. I'll let you review the conversion at your own pace, but it's something we will need to be aware of in the work we're going to review. Let's consider exercise 1. It states using radian measure, we've got to determine the lengths of the arc of a circle. So that'll be lengths of this arc here in the diagram, of a 2 meter radius. So this radius here is 2 meters. If the subtended angle is 300 degrees, this is the subtended angle. And part B, we're given a large gear wheel having a pitch circle diameter of 4 meters. So that's this distance across here. We're asked to calculate the pitch circle circumference using, again, radian measure. And this is the pitch circle circumference shown here. I encourage you to stop the presentation and attempt this exercise. The answers are shown here. For part A, it's shown in terms of pi or in terms of decimal. Same value, just expressed differently. For part B, the pitch circle diameter is shown here again in terms of pi and also decimal here. Here's exercise 1, part A. So we've got to find the length of the arc, shown here, of a circle of radius 2 meters. So the R is 2 meters. And the angle subtended is 300 degrees. Extracting the information from the question, the radius 2 meters, angle 300 degrees. The question wants us to use radian measure to find the arc length, so we're using S equals to R theta. Remember, in this equation the angle is always in terms of radians, so converting theta 300 degrees into radians, we multiply by pi and divide by 180 degrees. So in terms of radians, the angle is 5 pi upon 3. Inserting the values, then S is equal to the R, which is 2 meters in this case, and the angle theta in radians is the 5 pi upon 3. So that evaluates to 10 pi upon 3 meters, or evaluating 3 decimal places, that's 10.473 meters. So that's 10 multiplied by pi divided by 3. Here's exercise 1 continue, but part B, we're given in the question the pitch circle diameter, 4 meters, that's the diameter across here. We're asked to calculate the pitch circle circumference. This is shown here. So given the pitch circle diameter, D, 4 meters, dividing by 2, we can find the radius R, that's 2 meters. And remembering that in one revolution, there are 2 pi radians, then theta in this case is 2 pi. So the pitch circle circumference S is equal to the R theta. So that's 2 meters multiplied by 2 pi. So the pitch circle circumference is 4 pi meters, or calculating to 3 decimal places, that's 12.566 meters. Let's now consider angular velocity. So mean angular velocity is defined as the angular displacement theta per unit time t, where angular displacement, of course, equates to the angle turned through. So totally analogous to linear motion, where linear velocity is the linear displacement divided by the time taken, then angular velocity is the angular displacement divided by the time taken. The symbol used for angular velocity is commonly lowercase omega, that's a Greek letter. So in terms of symbols, the angular velocity, omega, is theta divided by t. And it's stated here the SI unit of angular velocity is radians per second, or can be written as radian seconds to the negative 1. And if we want to convert from an angular velocity in revs per minute, RPM, to radians per second, then in revs per minute multiplied by 2 pi upon 60. And if we want to convert from radians per second to RPM, then it's radians per second multiplied by 60 upon 2 pi. So they're shown for reference. Here's exercise 2. We're given a water wheel, rotates it 2 RPM. We've got to convert to radians per second. And we're given a turbine blade of a jet engine. It's rotating at 2032 radians per second. Got to convert that to RPM. The answers are shown in the bracket here. I would encourage you to stop the presentation and undertake exercise 2. Here's exercise 2, the solution. First of all, considering the water wheel. So 2 RPM multiplied by 2 pi upon 60. That evaluates to pi upon 15 radians per second, or the 3 decimal places 0.209 radians per second. Now considering the turbine blade rotating at 2032 radians per second, we multiply that by the conversion 60 upon 2 pi. So that's 19,404 RPM. Exercise 3. A flywheel's angular velocity is 25 radians per second. We've got to find the time taken to complete 4 revolutions. Answer is given in the bracket, approximately 1 second. I'd encourage you to stop the presentation and attempt this exercise, but I'll show you the full solution on the following slide. So exercise 3, here's the solution. We're given in the question the angular velocity, omega, is 25 radians per second. We've got to find the time taken to complete 4 revolutions. So the displacement, symbol capital N here, is 4 revs. We note that there are 2 pi radians in 360 degrees, or 1 revolution. So in 4 revolutions, the angular displacement, labelled theta here, is 4 multiplied by 2 pi. So 8 pi radians. Now from angular velocity is the angular displacement divided by the time taken. We can rearrange to find the time as required in the question. So the time is equal to theta divided by omega. Inserting the values, the time taken is approximately 1 second. Let's consider angular acceleration. So angular acceleration is defined as the change in angular velocity omega per unit time t. So as an equation, angular acceleration is equal to the change in angular velocity divided by the time taken. The usual symbol for angular acceleration in mechanical engineering is the Greek letter alpha. Note the notation for angular velocities. The initial angular velocity is omega I, of course in radians per second, and omega f as final angular velocity, again in radians per second. So in symbols form, angular acceleration alpha is equal to omega f minus omega I, that's a change in angular velocity, or divided by t, the time taken. Exercise 4. A disk is rotating with an angular velocity of 2,865 revs per minute. If it's uniformly accelerated, that's a constant acceleration, at a rate of 7.5 radians per second squared for 12 seconds, we've got to calculate the final angular velocity of the disk. The answer is given in the bracket here. I'd encourage you to stop the presentation and attempt this question based on the formula on the previous slide. Exercise 4 does involve some transposition. The full solution is shown on the following slide. Exercise 4, here's the solution. So extracting the information from the question, the initial angular velocity of the disk is 2,865 RPM. I've labelled that as uppercase omega here. We need to convert that into radians per second, so lowercase omega is 2,865 RPM multiplied by 2 pi divided by 60. That's the conversion into radians per second. So our initial angular velocity is 300 rads per second. The constant angular acceleration given in the question is 7.5 radians per second squared, so alpha stated here. And the time taken for this constant acceleration is 12 seconds, so t 12 seconds. So from the previous slides, we know that alpha is equal to the change in angular velocity divided by the time taken. So we have to transpose that for the final angular velocity. So rearranging the equation, the final angular velocity omega f is equal to the initial angular velocity added to alpha t. Inserting the values, the final angular velocity is 390 radians per second. Let's consider graphs of angular velocity plotted against time. And figure 2 shows such a graph. Here's the angular velocity on the vertical axis. Notice it's in radians per second. And here's the time plotted on the horizontal axis in seconds. And as mentioned before, there is direct analogy between a linear velocity time diagram and an angular velocity time diagram. In a linear velocity time diagram, the area under the graph relates to the displacement, or sometimes the distance travelled in meters. With an angular velocity time diagram, the area under the graph is the angular displacement, theta. So this area shown shaded here is angular displacement, and that's in radians. With linear motion velocity time diagrams, the gradient of the line relates to the linear acceleration or deceleration. With an angular velocity time diagram, the slope or the gradient of the graph relates to the angular acceleration, alpha. So the slope here, or the gradient, is the angular acceleration. Notice that's in radians per second squared. So again, direct analogy between linear and angular motion. If you understand the concept of linear motion, then that strongly underpins the concept of angular motion. Here's the angular velocity time diagrams continued. So again, as with the linear motion graphs, where we develop some equations related to areas under the graph and slope of the line, we can do exactly the same thing with the angular motion diagrams. So we can show from the graph that the angular displacement, theta, is the final angular velocity plus the initial angular velocity divided by 2, or multiplied by the time t. That's essentially calculating the area under the graph. And we can show that the angular acceleration, alpha, which is the slope or the gradient of the graph, is calculated from the formula omega f minus omega I, or divided by t. And that's the gradient of this line here. So if we want to compare linear and angular motion equations, then here they are side by side. Always remember that these equations relate to uniformly accelerated situations where a constant acceleration is applied. So on the left hand side here we have the linear motion equations, typical v is equal to u plus at. In terms of the angular motion equation, that becomes omega f is equal to omega I plus alpha t. So as I keep emphasizing, if you understand the application of linear motion equations, then it's essentially the same process applying the angular motion equations. You can see the similarity with the remaining equations here, all derived from the velocity time diagrams. The previous linear motion equation presentation shows more detailed derivation of the linear equations, but it's the same process for deriving the angular motion equations. Here's the full nomenclature for reference. Exercise 5. After being balanced, a grinding wheel, shown in the sketch here, was located on a spindle and accelerated to an operating speed of 2,800 revs per minute. And that occurred in 10 seconds from where it was dressed. In other words, trying to return the grinding wheel to its original sharpened condition. After dressing the grinding wheel, the power to the wheel was switched off and the wheel was allowed to come to rest freely. The deceleration of the wheel was assumed to be uniform, in other words, constant. If the wheel was running for a total of 5 minutes and it took 2 minutes for the wheel to come to rest, we've got to determine for the wheel the following. A, the angular acceleration of the wheel. B, the angular retardation of the wheel or deceleration of the wheel. And the total number of revolutions made by the wheel during the 5-minute duration. For reference, the answers are shown here. I would encourage you to start the presentation and attempt this question. Carefully read the question, extract the information from the question, undertake conversions as required, and then apply the appropriate formulae for calculating the angular acceleration and the angular retardation. Don't forget accelerations relate to gradient of the line on the velocity time diagram, and the total number of revolutions relate to the area under the angular velocity time diagram. The full solution is shown on the following slides. Here's exercise 5 solution. Notice I've drawn a velocity time diagram to begin with, and I would always encourage you to draw a velocity time diagram. It doesn't have to be to scale, just sketch proportionally is reasonable. On the vertical axis I have my angular velocity in radians per second, and notice I converted the angular velocity in the question of 2,800 rpm, shown here, capital omega, into radians per second, lowercase omega, using our standard conversion of 2 pi upon 60. So 2,800 rpm becomes 293.22 radians per second. And extracting the time from the question, time for acceleration was 10 seconds, shown here. That was to achieve the above angular velocity. The total time taken was 5 minutes. Notice I've converted that into seconds. There are 60 seconds in a minute, so total time taken is 300 seconds. And the deceleration was 2 minutes. Again, converting that to seconds, 120 seconds. So I've added these durations to the velocity time diagram on the horizontal axis. 10 seconds for the acceleration phase, 300 seconds for the overall time taken, and 120 seconds for the deceleration phase. Knowing these times, I can now work out the time taken in the constant velocity phase of the diagram, and also when the deceleration phase commenced. Exercise 5 solution continued. Part A of the question, the angular acceleration. From the standard formula we've used, angular acceleration is the final angular velocity minus the initial angular velocity, all divided by the time taken. From our diagram, our final angular velocity is shown here, 293.22 radians per second. The initial angular velocity is 0, and that's all divided by 10 seconds. So the constant angular acceleration is 29.2 radians per second squared. Part B, to calculate the angular retardation or deceleration. Again, alpha here is omega f minus omega I divided by the deceleration time. Notice the final angular velocity for the deceleration phase, shown here, is 0, but the initial angular velocity of the deceleration phase is the 293.22 radians per second. So that's all divided by the time taken for the deceleration phase, 120 seconds. Notice that calculates to be a negative value, negative 2.4 radians per second squared. Negative because we've got a negative gradient on our velocity time diagram. The acceleration phase is a positive gradient. Just for reference, I've labelled the phases of the velocity time diagram. This is the acceleration phase. This is the deceleration phase. This is the constant velocity phase along here. Exercise 5 solution continued. So part C, we've got to calculate the total number of revolutions. So that's basically the angular displacement. That's the area under the graph. Basically, we calculate the area of this triangle here, which is this calculation here. Base times vertical height divided by 2. It's the area of a triangle. We add that to the area of the rectangle, shown here. That's this calculation here. Finally, we add the area into this triangle, shown here. This is this calculation here. And do remember we're calculating the angular displacement theta, and the area under the velocity time diagram as shown will be in radians. So it's 68,906.7 radians. Don't forget, area under the graph is in radians. Convert that into revolutions, then it's the angle turned through in radians divided by 2 pi. There are 2 pi radians in one revolution. So that's approximately 10,967 revolutions. The next two slides show some very useful relationships that can be derived, and the full proofs are shown here. To keep this presentation shorter, I'm just going to show the final relationships, and in a short separate presentation I'll actually go through in more detail the proof that are shown here. So basically what we're considering on this slide is a relationship between linear and angular velocity. The full proof is shown here, but I'm going to jump to the final solution here in this bolded box. And this is an extremely useful relationship that occurs within mechanical engineering. Basically what we have here is a relationship between linear velocity, v, and angular velocity, omega. V is equal to omega r. That is a particularly useful relationship, and one we will use in this presentation and also in further work. Here's the relationship between linear and angular acceleration this time. Again, a proof here from a standard textbook is shown. I won't go through this in any detail now. I'll put this into a separate presentation, but I'll highlight to you the final equation shown here, which relates linear acceleration a to angular acceleration alpha by the equation a equals alpha r. And again, that's a very useful equation that underpins lots of work in kinematics and dynamics at higher level study. So for the purpose of this presentation, we'll accept that relationship and use the equations, but I will outline the full proof in more detail in a separate short presentation. Exercise 6. A car has a linear velocity of 10 meters per second. We're asked to determine the angular velocity of the road wheels if they have a roll-in diameter of 600 millimeters. So the roll-in diameter is labelled as D here in the sketch. The answer is given in the bracket. I would encourage you to stop the presentation and attempt exercise 6 using the formula derived previously between linear and angular velocities, but a solution is shown on the following slide. Exercise 6 is the full solution. We're given in the question the car's linear velocity is 10 meters per second, shown here, v is equal to 10 meters per second. We're calculating the angular velocity of the road wheels, and the rolling diameter of the wheels is 600 millimeters, so the road wheel diameter, capital D, I've converted to meters here, it's 0.6 meters. So of course the radius in this case is the diameter divided by 2, so 0.3 meters is the radius of the road wheels. So knowing that linear velocity, v, is equal to the angular velocity multiplied by the radius. To find the angular velocity we simply transpose, so omega is the linear velocity v of the car, that's 10 meters per second, divided by the radius of the road wheel, which is 0.3 meters from above. So evaluating the angular velocity is 33 1/3 radians per second. Well, the answer in the sheet shown to 2 decimal places, 33.33 radians per second. So that's an illustration of calculating the angular velocity given the linear velocity. Exercise 7. A vehicle moving with a uniform velocity of 12 meters per second is brought to rest in 3 seconds. If the road wheels are 0.6 meters diameter, we've got to calculate the number of revolutions made by the road wheels in bringing the vehicle to rest. So this question will involve considering the relationship between linear and angular velocity again, and then calculating the area under the velocity time diagram to find the displacement. I would encourage you to sketch the velocity time diagram for this situation, as I think that aids clarity of the problem. The answer is shown here in the bracket. I'd encourage you to start the presentation and attempt exercise 7, but I'll show you the full solution on the following slide. Exercise 7, full solution here. So extract information from the question. The uniform velocity v is given as 12 meters per second, shown here. The time taken to bring the vehicle to rest is 3 seconds, shown here. The road wheels are stated as 0.6 meters diameter, so diameter 0.6 meters, and I've calculated the radius here, it's obviously diameter divided by 2, so 0.3 meters. Now we know from our previous work the angular velocity omega is equal to linear velocity divided by the radius. We're given a linear velocity in the question, that's 12 meters per second. We just calculated the radius as 0.3 meters. So the angular velocity is 40 radians per second. Here's a sketch of my angular velocity time diagram. Vertical axis I have my angular velocity omega, so that's the 40 radians per second. And we know from the question the time taken to bring the vehicle to rest was 3 seconds. So that's on my horizontal axis. T is in seconds. Remember, the area under a velocity time diagram is displacement. In this case, the displacement is in radians. So the angular displacement theta is basically the area under the graph. So that's simply going to be the angular velocity multiplied by the time divided by 2. Area of a triangle, base times height divided by 2. Insert in the values. The angle turned through in bringing the vehicle to rest is 60 radians. That's 9.549 revolutions. Exercise 8. In an experiment on a flywheel shown in figure 3, here's figure 3, here's the flywheel front elevation and the flywheel side elevation. A mass shown here is moved downwards through a distance of 1.5 meters before the string detaches itself from the spindle. This is the spindle shown here in the front elevation, here in the side elevation, and this is the string that attaches the mass to the spindle or shaft on which the flywheel sits. The acceleration of the flywheel was measured at the rim and was found to be 2.6 meters per second squared. That's a linear acceleration. We're asked to determine part A, the angular acceleration for the flywheel, and part B, the angular velocity of the flywheel at point of release of the string. So in other words, when the string has unwrapped itself from the shaft or the spindle, as the mass moves downwards, the mass will eventually fall to the floor. Part B wants the angular velocity of the flywheel as the string, and so mass is released from the shaft. Now in the question we're given the diameter of the spindle or shaft and also the diameter of the flywheel. Quite a complicated little scenario here. This actually relates to a practical experiment to find moment of inertia of the flywheel, which is beyond this particular presentation. But the kinematic aspect, in other words working out the angular acceleration, angular velocity, are covered by the equations we've defined in this presentation. The answer for the angular acceleration of the flywheel, the angular velocity in RPM are shown here. If you think you can attempt this question, I would encourage you now to start the presentation and attempt it, but I'll show you the full solutions on the following slides. Just for your interest, this is the actual flywheel experiment. This is the flywheel shown here. And this is the shaft or a spindle here, and you can see the string is wrapped around the spindle. It's actually located on a very small hook, which is just shown here. And this is the hanger on which the mass is placed. So essentially, as the hanger is released, it starts to fall through some distance. That distance relates to the actual length of the string in this particular instance. And once the string is unwound from the shaft, the mass falls to the floor. So that's the basic experiment that's undertaken here. Here's a sketch of the two scenarios of the initial position of the flywheel and the final position of the flywheel. The left-hand side is position 1. This is where the mass is being held in position. The string is wrapped around the spindle, and the mass is about to be released so that it can fall vertically downwards under the effect of gravitational acceleration. On the right hand side, in position 2, this is where the mass has fully unwound itself and now is about to be released from the spindle as it falls to the floor. So the flywheel is no longer being driven by the effect of the mass connected to the string wrapped around the spindle. To answer part A of the question, we have to calculate the angular acceleration of the flywheel alpha given the linear acceleration of the flywheel A at the flywheel's rim on release of the mass from the spindle. And after the acceleration has occurred, we have to find the final angular velocity of the flywheel, labelled omega. So let's consider the thought process required here to help us solve this problem. First of all, what information are we given in the question? Well, we're given the linear distance travelled by the mass, so that would be s. And we're also given the diameter of the shaft, or the spindle, and we're given the diameter of the flywheel. So if we need to find the radius for either of those items, then we can find r. So we have r if required. Also we're given in the question, we're given the linear acceleration of the flywheel A. What does the question want us to find? Well, in part A, it wants us to find the angular acceleration, that symbol alpha. So straight away I can see I could find the angular acceleration from this equation, A is equal to alpha r. The final angular velocity is omega f, and it occurs in this equation, and this equation. It doesn't occur in this equation, so I can ignore this one. And also notice in these two equations, here and here, time is required. And time is not given in the question, so I'm going to ignore those two equations as well. So that leaves me with this equation here. Omega f, I'm trying to find, is here. So this equation would need me to know the initial angular velocity, which I would assume to be 0. So I have that. And it wants me to know the angular acceleration, which I know from this equation above. So I have that. And it also needs me to know the angle turned through in radians, the displacement. And I can find that from this equation here. So knowing theta from the s equals to r theta formula, I can then place it into here. And then simply square rooting both sides in this case, I'll find the final angular velocity of the flywheel. So I don't know if that helps you, but that's my little thinking steps based on the equations we've derived in this presentation. So exercise 8, here's the solution. First of all, extract information from the question. We know that the mass moves downwards a distance of 1.5 meters. So I've labelled that as S here, 1.5 meters. We know from the information given the diameter of the flywheel is 300 millimeters. denoted that as dW here. So 300 millimeters, I'm converting that straight into meters, so 0.3 meters. And we know the diameter of the spindle or the shaft is 25 millimeters, so ds 25 millimeters. Again, convert it to meters, 0.025 meters. The question has given us the acceleration of the flywheel, 2.6 meters per second squared, so A here, 2.6 meters per second squared. Notice the linear acceleration stated is at the flywheel's rim, i.e. the outer radius of the flywheel. From the above geometry we can find the radius of the flywheel, that's just the diameter of the flywheel divided by 2, so 0.15 meters. And we can find the radius of the spindle or shaft, again that's the shaft diameter divided by 2, so 0.0125 meters. So there's some basic information extracted from the question. Exercise 8, solution continued here. Just repeated some of the information from the previous slide for convenience. So for part A, we've got to find the flywheel's angular acceleration, assume constant here. So we know that alpha, the angular acceleration, is A divided by R. A is the linear acceleration, R is the radius of the flywheel in this case. So the angular acceleration at the rim of the flywheel is 2.6 meters per second squared, and the outer radius of the flywheel is 0.15 meters. So evaluating the angular velocity of the flywheel is 17⅓ radians per second squared. In part B, we've got to find the flywheel's angular velocity, this time at the point of release. So from our previous plan of attack for solving this problem, the first thing we need to do is calculate the angle turn through in radians. We find that from radian measure, S equals to R multiplied by theta. Rearranging for theta, the displacement, that's simply S divided by R. We know the distance travelled by the mass is 1.5 meters given in the question, and we know the radius of the shaft or the spindle is 0.0125 meters. That evaluates to an angle turn through of 120 radians. So finally, from the equations of motion, we're going to use omega f squared equals to omega I squared plus 2 alpha theta. To find omega f, we simply square root both sides. Inserting the values, the initial angular velocity is assumed to be 0, it starts from rest. The angular acceleration is calculated above, 17⅓, and we've just evaluated the angle turn through theta as 120 radians. We can evaluate the final angular velocity at 64.49 radians per second. Just notice I convert this to RPM to find the final answer. So the angular velocity is approximately 616 revs per minute. Here are some questions related to angular motion. Question 1 requires us to convert angular velocities from RPM to radians per second, whilst question 2 requires us to convert angular velocities from radians per second to revolutions per minute. Question 3, a slightly thought-provoking question here. We're asked to calculate the magnitude of the angular velocities in radians per second of the second, minute and the hour hands of a clock. The answers to all questions are stated in the bracket beneath each question. To help you with the conversions, you may find the use of unity brackets to be beneficial. I'd encourage you to start the presentation and attempt questions 1 to 3. Questions continued. Here's question 4. The scenario given here is an electric motor commences speed from rest, reaches a running speed of 1400 RPM in 1.2 seconds. We've got to calculate the angular acceleration of the motor's armature, assuming the acceleration is uniform. We've also got to calculate the number of revolutions turn through during the acceleration phase. In question 5, the propeller of a model aero engine has a 200 millimeters tip to tip length, so from here to here is 200 millimeters. We've got to calculate the linear velocity of the tip of the propeller when the engine is rotating at 16,000 RPM. If the engine is brought to rest in 3 seconds, we've got to determine the angular retardation, deceleration in other words, assuming the retardation is uniform. Answers again stated in the brackets. Again, I would encourage you to always sketch the velocity time diagrams to help with the understanding of the particular question and the scenario given. Here are further questions. Question 6, question 7, I'll let you read and attempt at your own pace. And question 8 and question 9. And again, I'll let you review these at your own pace. Answers are stated in the brackets here. For reference, here's the bibliography used to help generate this presentation, and I hope this has been of interest to you, and thank you for viewing.